Right now, while you're watching this video, hundreds of asteroids large enough to devastate entire regions are lurking in a zone where our telescopes can't see them. We're talking about objects 700 meters across, twice the height of the Empire State Building, hiding in plain sight, and we won't know they're coming until it's too late. The world is obsessing over 3IATLAS, that interstellar visitor currently 126 million miles away, moving harmlessly through our solar system. Scientists are tracking its every move, telescopes around the globe monitoring its fragmentation, Avi Loeb speculating about its origins. Meanwhile, a far more immediate threat goes almost completely ignored. A massive blind spot in Earth's asteroid detection system, created by the one object we depend on for survival, the Sun itself. This isn't speculation. This isn't fear-mongering. On September 27th, 2025, just weeks ago, astronomer Scott Shepherd discovered an asteroid that had been hiding in the Sun's glare, already in Earth's vicinity, completely undetected until that moment. The object, designated 2025 SC79, measures 700 meters in diameter. To put that in perspective, the asteroid that exploded over Tunguska, Siberia, in 1908, flattening 200 square kilometers of forest, was estimated at only 50 to 100 meters across. The object Shepherd found is 7 to 14 times larger. Stay with me, because here's where this gets deeply disturbing. Congress mandated in 2005 that NASA must detect 90% of near-Earth asteroids larger than 140 meters by 2020. We missed that deadline. Badly. As of today, November 2025, we've only catalogued about 40% of these objects. NASA now admits it might not achieve the 90% goal until 2030 or later. And the Space Telescope specifically designed to solve this problem, NEO Surveyor, has been delayed, defunded, and deprioritized so many times that its cost has ballooned from $500 million to $0.2 billion, and its launch date has slipped from 26 to 28, maybe later. This is the only program NASA is legally required to complete, yet we keep pushing it back. And every day we delay, Earth remains vulnerable to thousands of undetected asteroids, some large enough to trigger a global catastrophe. Before you comment, "Don't Look Up was just a movie," drop your location and local time in the comments. I want to know where you all are watching from as we unpack this genuinely terrifying problem. And if this investigation into the blind spot that could end civilization sounds urgent enough to deserve more attention than a distant interstellar comet, hit that subscribe button. This channel exists to examine the cosmic mysteries that actually matter for our survival. September 27th, 25, Cerro Tololo Inter-American Observatory, Chile. Scott Shepherd, a Carnegie Science astronomer renowned for discovering dozens of moons around Jupiter, Saturn, Uranus, and Neptune, was conducting one of the most technically challenging observations in astronomy. Twilight survey. Let me explain what that means. Most asteroid hunting happens at night, when telescopes scan the dark sky for moving objects illuminated by sunlight. Simple enough, but there's a problem with that approach. It only finds asteroids that spend most of their time in regions of space away from the Sun. Asteroids whose orbits keep them between Earth and the Sun, the so-called Attira and Vatira populations, are almost never in the night sky. They're only visible during twilight, that brief window after sunset or before sunrise, when the sky is dark enough to take images, but the Sun is still close enough to the horizon that you can see objects near it. This is not a large window. Ground-based telescopes have less than 30 minutes. That's it, 30 minutes of usable observing time. And during those 30 minutes, astronomers like Shepherd face extraordinary challenges. First, they must peer through the thickest part of Earth's atmosphere, right at the horizon, where gases cause light to flicker and diffuse. Second, they're racing against the clock. The Sun is either setting below the horizon, ending the observation window, or rising above it, making observations impossible. Third, they must avoid saturating their detectors with sunlight, which means they can't point too close to the sun, even during twilight. Shepard was using the dark energy camera DCAM, mounted on the National Science Foundation's Blanco 4-meter telescope. DCAM is a 570 megapixel CCD imager originally designed for the dark energy survey, but it's become one of the most powerful tools for twilight asteroid hunting because it can detect extremely faint objects while covering a relatively large field of view. On that night in late September, Shepard's images captured something moving against the background stars. After confirming the detection with follow-up observations from NSF's Gemini Observatory in Hawaii and Chile, plus Carnegie Science's Magellan telescopes in Chile, the reality became clear. This was a large near-Earth asteroid that had been completely unknown until that moment. The Minor Planet Center, the International Astronomical Union's clearinghouse for asteroid and comet observations, issued a circular on October 15, 2025, officially designating the object 25 SC79. Here's what we learned about 25 SC79. It's approximately 700 meters in diameter, tiny 300 feet, or roughly twice the height of the Empire State Building. Its orbital period is just 128 days, making it the second fastest asteroid in the solar system, after only 2021 PH27 and tied with 2025 GN1. It belongs to the Atira group, meaning its orbit stays mostly inside Earth's orbit. And most critically for our story, it had been hiding in the sun's glare, undetected, possibly for its entire existence as an Earth-crossing object. Now, before anyone panics, 2025 SC79 will make no close approaches to Earth for the foreseeable future. This particular asteroid isn't going to hit us. But that's not the point. The point is what 2025 SC79 represents. Proof that objects large enough to cause continental-scale destruction can remain completely unknown despite decades of asteroid surveys, simply because they orbit in a region where our detection systems can't see them. Scott Shepard put it bluntly in Carnegie Science's press release: the most dangerous asteroids are the most difficult to detect. He explained that most asteroids enter telescopes' detection range in the dark of night, but asteroids lurking near the sun are only visible at twilight, creating enormous detection challenges. These twilight asteroids could pose serious impact hazards if they approach Earth, precisely because we can't see them coming. Think about that. The most dangerous asteroids, the ones most likely to hit us without warning, are systematically the hardest ones to find. It's not a minor observational inconvenience. It's a fundamental blind spot in our planetary defense system. And 2025 SC79 isn't even the first example. In 2021, Shepard discovered 21 PH27, another Atira asteroid hiding in twilight. That object holds the record for the shortest orbital period of any asteroid, just 113 days. It gets so close to the sun that its surface temperature reaches 500 degrees Celsius, hot enough to melt lead. These discoveries keep happening because astronomers like Shepard are willing to do the incredibly difficult work of twilight surveys. But here's the problem. Ground-based twilight surveys can only scratch the surface. They're limited by geometry, by atmospheric interference, by that 30-minute window, and by the sheer brightness of the sun. No matter how good our ground-based telescopes get, there will always be regions of space near the sun that we simply cannot observe from Earth's surface. Let me give you the geometry. From Earth, we can only see objects in twilight when they're at a certain angle from the sun, far enough that the sky is dark, but close enough that the sun hasn't completely set or risen. But asteroids don't care about our observing constraints. An asteroid whose orbit keeps it at a smaller angle from the sun, closer in terms of apparent position in the sky, remains completely invisible from Earth. It's in the blind spot. And that blind spot isn't small. We're talking about a huge cone of space, extending millions of miles from the sun. that ground-based telescopes simply cannot survey effectively. Space-based telescopes don't help much either. Instruments like the Hubble Space Telescope and the James Webb Space Telescope avoid pointing anywhere near the Sun. This isn't an arbitrary restriction. It's a matter of survival for the telescope. Point Hubble, or JWST, too close to the Sun, and you risk overwhelming the detectors with radiation, causing permanent damage, or, in the worst case, heating the spacecraft to dangerous temperatures. These telescopes cost billions of dollars and represent decades of work. We don't point them at the Sun. So we have a situation where ground-based telescopes can't effectively survey near the Sun, and space-based telescopes in Earth orbit won't survey near the Sun. That leaves a massive detection dead zone. And inside that dead zone, asteroids like 2025 SC79 can lurk, undetected, potentially for years or decades. Now multiply 2025 SC79 by potentially hundreds of similar objects. Astronomers estimate there are thousands of undiscovered near-Earth asteroids in the 140-meter plus size range, the size Congress mandated we find. How many of those are Atiras and Vatiras, hiding in the Sun's glare? We don't know. By definition, we can't see them to count them, but based on the discovery rate of objects, like 2025 SC79 and 2021 PH27, we know they're out there. And here's the truly chilling part. The problem extends beyond just the Atira population. Even asteroids with more conventional orbits can approach Earth from the direction of the Sun, rendering them invisible during their final approach. You don't need an asteroid that spends its entire orbit inside Earth's orbit. You just need an asteroid whose trajectory brings it toward Earth at the wrong angle, sunward, and suddenly our entire detection system is blind. This isn't theoretical. This has already happened, and not with some tiny pebble, but with an object that injured 1,500 people. February 15th, 2013, Chelyabinsk, Russia, 9:20 a.m. local time. A 20-meter asteroid, traveling at approximately 19 kilometers per second, entered Earth's atmosphere completely undetected. Nobody saw it coming, not NASA, not the Russian Space Agency, not amateur astronomers, not the network of professional surveys that had been scanning the sky for dangerous asteroids for years. Zero warning. The meteor's radiant, its source direction in the sky, was close to the Sun. It approached from the southeast, from the direction of sunrise. By the time anyone could have possibly detected it visually, it was already entering the atmosphere, beginning its catastrophic deceleration from hypersonic speeds. The explosion occurred at an altitude of 23.3 kilometers above the city. The energy release was equivalent to approximately 500 kilotons of TNT, roughly 30 times the yield of the atomic bomb dropped on Hiroshima. The shockwave propagated outward at supersonic speed, and when it reached the ground, it shattered windows across 6 cities. 1,291 people required medical treatment. Most injuries came from flying glass, windows blown inward by the shockwave, turning into deadly fragments. Over 7,200 buildings suffered damage. The intense light from the meteor, momentarily brighter than the Sun, produced 180 cases of eye pain and 70 instances of temporary flash blindness. 20 people reported ultraviolet burns, similar to severe sunburn, intensified by reflection of snow on the ground. One victim, a 52-year-old woman, suffered a broken spine and required transport to Moscow for treatment. The total damage exceeded $33 million for a 20-meter asteroid, an object the size of a 6-story building, but small enough that most asteroid surveys would have struggled to detect it until it was already very close to Earth. Now here's what should keep you up at night. 2025 SC79, the asteroid Scott Shepherd discovered in September, is 700 meters across. That's 35 times larger in diameter than the Chelyabinsk meteor. But asteroid damage doesn't scale linearly with size. It scales with volume, with mass, with kinetic energy. A 700-meter asteroid carries thousands of times more kinetic energy than a 20-meter object. The impact of something like 2025 SC79 wouldn't just break windows in a few cities, it would devastate an entire region on a continental or potentially global scale, depending on where it hit. And 2025 SC79 was hiding in the same blind spot that concealed the Chelyabinsk meteor, the sun's glare. Let me break down exactly why this blind spot exists and why it's so difficult to overcome. The physics of the problem starts with basic geometry and radiometry. From Earth's surface, the sun is extraordinarily bright, apparent magnitude -26.74, far brighter than any other natural object in the sky. The full moon, for comparison, is magnitude -12.74, which means the sun is about 400,000 times brighter than the full moon. Venus at its brightest is magnitude -4.9. The brightest stars are around magnitude -1.5 to +1. Asteroids, even large ones, are typically magnitude +15 to +22 when near Earth, thousands to millions of times fainter than the naked eye can detect. When you're trying to image an object a million times fainter than the background glow, you need pristine observing conditions. You need dark skies, minimal atmospheric interference, and absolutely no light contamination from bright sources. During twilight, you have none of these advantages. Ground-based telescopes attempting twilight surveys face a brutal set of constraints. First, timing. The sun must be far enough below the horizon that the sky has darkened sufficiently for the telescope to open without saturating the detectors, but not so far below the horizon that objects near the sun have also set. This creates the 30-minute window I mentioned earlier. Second, atmospheric thickness. When you look at the horizon, you're looking through the maximum thickness of Earth's atmosphere, roughly 38 times thicker than when you look straight up. All that extra air scatters sunlight, creating a bright background glow that makes faint objects harder to detect. It also causes astronomical seeing, the twinkling and distortion of images due to turbulence in the atmosphere, to be at its worst. Stars and asteroids flicker and blur, reducing the precision with which you can measure their positions and brightnesses. Third, absorption and scattering. Earth's atmosphere absorbs many wavelengths of light, particularly in the infrared, where asteroids emit thermal radiation. During twilight, when you're looking through the thickest part of the atmosphere, this absorption is maximized. The asteroid signal is weakened, and the background noise from scattered sunlight is amplified. Signal-to-noise ratio plummets. Fourth, safety margins. Most telescopes have strict rules about how close to the sun they're allowed to point, even during twilight. Accidentally, point too close, and you could damage expensive detectors. So observers add buffer zones, further limiting the searchable region of sky. The combined effect of these constraints is that ground-based twilight surveys can only probe a small fraction of the sun's vicinity. They're limited to objects at solar elongations, angular distance from the sun, greater than roughly 45 to 60 degrees, and even then only during that 30-minute window twice per day. Objects closer to the sun remain invisible, and this is where the Atira and Vatera populations become such a problem. These asteroids have orbits that keep them inside Earth's orbit, meaning they spend most or all of their time at small solar elongations, as seen from Earth. They're systematically hidden in the blind spot. The only times they might be visible are during brief windows when they reach maximum elongation, their farthest angular distance from the sun as seen from Earth, and even then, they're only visible during twilight. Scott Shepherd's twilight surveys using DECAM have been remarkably successful at finding these hidden asteroids, but he's working against enormous odds. DECAM has a large field of view, about 2.2 square degrees, which helps, but the searchable region near the sun during twilight is many thousands of square degrees. And he only gets 30 minutes per day, In practice, more like 20 minutes of truly usable time, split between evening and morning twilight. Weather, moon phase, and telescope scheduling constraints reduce the actual number of nights available for observations. The result is that each region of sky near the Sun gets surveyed maybe a few times per year at best. For comparison, the Pan-STARRS survey, one of the most prolific asteroid-finding telescopes, scans the entire accessible sky every few days when conditions are good. It has found thousands of near-Earth asteroids, but Pan-STARRS doesn't do twilight observations. It can't reach objects near the Sun. So we have comprehensive coverage of most of the sky, and almost zero coverage of the region where the most dangerous asteroids hide. Let's talk about space-based observations. Why don't we just put a telescope in orbit and point it toward the Sun? We have space-based telescopes. The Hubble Space Telescope has been operating since 1990. The James Webb Space Telescope launched in 2021. The Roman Space Telescope is scheduled to launch in 2027. These are extraordinary instruments, capable of detecting objects a billion times fainter than the naked eye can see. Surely they could spot asteroids near the Sun, right? No, because they're not designed for that task, and they can't be repurposed for it. Hubble orbits Earth at an altitude of about 540 kilometers. From that vantage point, it has essentially the same view of the Sun as we do from Earth's surface. It's in Earth orbit, so the Sun still appears as an intensely bright object that must be avoided. Pointing Hubble at the Sun, or even near the Sun, would flood its detectors with light, potentially causing permanent damage. The spacecraft also has thermal constraints. Its instruments are designed to operate in the cold of space while looking away from the Sun. Point toward the Sun, and you risk overheating. JWST is even more sensitive to heat and light. It operates at L2, the second Lagrange point, about 1.5 million kilometers from Earth, on the side away from the Sun. Its massive sun shield keeps its infrared detectors cooled to about 40 Kelvin, cold enough that the detector's own thermal radiation doesn't overwhelm the faint signals from distant galaxies. The sun shield always faces the Sun, and the telescope always faces away. Turning JWST to point at or near the Sun would require rotating the spacecraft so that sunlight hit the cold side, which would quickly heat the instruments to temperatures where they couldn't function and might cause permanent damage to the delicate mechanisms and detectors. Even if you wanted to use these telescopes for asteroid hunting near the Sun, which you don't because they're already fully subscribed for other science, you couldn't. They're physically incapable of performing that observation. What about dedicated asteroid hunting satellites? We've had those too. The WISE spacecraft, launched in 2009, surveyed the entire sky in infrared wavelengths and discovered thousands of asteroids. It was later reactivated as NEO-WISE and continued asteroid hunting until it was decommissioned in 2024. NEO-WISE was fantastic for finding asteroids in the outer solar system and in regions away from the Sun, but it was in low Earth orbit, so it faced the same constraints as Hubble. It couldn't safely observe close to the Sun. The fundamental problem is this: to effectively survey near the Sun, you need a telescope specifically designed for that task. It needs to be positioned where it can view objects near the Sun without being blinded by sunlight. It needs detectors that can operate in the intense radiation environment near the Sun. It needs a thermal design that can handle the heat, and it needs to operate in infrared wavelengths, because thermal emission from asteroids isn't drowned out by sunlight the way reflected visible light is. Such a telescope doesn't currently exist in operation, but one has been designed. It's called NEO Surveyor, and it's been repeatedly delayed and defunded, despite being the only program NASA is legally mandated to complete. Before we get to that infuriating story, let's establish exactly how big this blind spot problem is, because it's not just about asteroids hiding in stable orbits inside Earth's orbit. It's about the simple fact that any asteroid approaching Earth can be invisible during part of its trajectory, depending on the geometry. In 2023, an asteroid designated 2023 NT1 made a close approach to Earth. The object is about 50 to 60 meters across, roughly 3 times the size of the Chelyabinsk meteor. It passed within about 3,600 kilometers of Earth on July 13, 2023. That's closer than many satellites, and we didn't detect it until July 15th, 2 days after it had already passed us. Where was it hiding in the sun's glare? This keeps happening. In January 2023, Asteroid 2023 BU passed within 2,200 miles of Earth's surface, closer than geosynchronous satellites. It was only detected a few days before its closest approach. Objects as large as an Olympic swimming pool can approach to extremely close range, and our detection systems don't see them until they're almost on top of us. Tarek Daly, a planetary scientist at Johns Hopkins Applied Physics Laboratory, put it bluntly. We lack knowledge about the majority of asteroids that could lead to local or regional destruction. And here's the critical distinction that makes this problem so much more urgent than tracking distant interstellar visitors like 3IATLAS. Near-Earth asteroids cross our orbit regularly. They're in the neighborhood. They're on trajectories that bring them close to Earth on predictable timescales. 3IATLAS is 126 million miles away at its closest approach to Earth, on a hyperbolic trajectory that will take it out of the solar system forever. It's been fully tracked since its discovery in July 2025. We know exactly where it is, where it's going, and that it poses zero threat to Earth. The twilight asteroids, the objects hiding in the sun's glare, are different. They're close. Some of them cross Earth's orbit, and most of them remain undetected. We're flying blind through a cosmic shooting gallery, and some of the bullets are 700 meters across. December 22, 2005, President George W. Bush signed into law the NASA Authorization Act of 2005, Public Law 109-155. Buried in that legislation was Section 321, also known as the George E. Brown Jr. Near-Earth Object Survey Act. The law was simple and unambiguous. It directed NASA to implement a near-Earth object survey program to detect, track, catalogue, and characterize the physical characteristics of near-Earth objects equal to or greater than 140 meters in diameter. The deadline, 90% completion within 15 years. That meant by December 2020, NASA was legally required to have found and catalogued 90% of all near-Earth asteroids 140 meters or larger. Why 140 meters? Because that's the threshold where an impact transitions from a local catastrophe to a regional or potentially continental disaster. An asteroid 140 meters across carries enough kinetic energy to devastate an area the size of a major metropolitan region or create an unprecedented tsunami if it struck an ocean. Objects smaller than 140 meters, like the Chelyabinsk meteor, can still cause significant damage and casualties, but they're unlikely to threaten civilization. Objects larger than 140 meters start to enter the range where they could kill millions of people and disrupt global infrastructure. Scientists estimate there are approximately 25,000 near-Earth asteroids in the 140 meter plus size range. The 2005 mandate required NASA to find 22 to 500 of them by 2020, find them, track them, characterize their orbits precisely enough to predict if and when they might threaten Earth. We missed the deadline, badly. As of November 2025, 2 decades after the mandate was issued and 5 years past the deadline, we've catalogued somewhere around 10,000 to 11,000 of these objects. That's roughly 40 to 44%. We're not even halfway there. NASA now projects it might reach the 90% goal sometime in the 2030s, using current ground-based surveys. Maybe. That's 3 decades behind schedule. And the most frustrating part, we have the technology to do this. We know exactly what needs to be built. Engineers have designed the telescope, selected the instruments, calculated the orbits, planned the mission. The telescope that could finally fulfill the congressional mandate exists on paper and is now being built. It's called NEO Surveyor, and its history is a masterclass in how bureaucratic delays, budget cuts, and shifting priorities can undermine even legally mandated programs. NEO Surveyor began its life in the early 2010s as NEOCAM, the Near-Earth Object Camera. The concept was straightforward. Put an infrared telescope at the L1 Lagrange point between Earth and the Sun, where it could continuously scan the inner solar system for asteroids, including those hiding in the Sun's glare. The mission was proposed multiple times to NASA's Discovery program, which funds small to medium-sized planetary science missions. NEOCAM was consistently rated as scientifically excellent, and it was consistently not selected for funding. In 2019, after years of proposals and rejections, NASA elevated the mission from the Discovery program to become a dedicated planetary defense mission. It was renamed NEO Surveyor and given a target launch date in the mid-2020s. Finally, it seemed, the mission that could fulfill the congressional mandate would get the resources it needed. Then the delays started. Fiscal year 2022 saw significant budget cuts to NASA's Planetary Science Division due to cost overruns on other missions. NEO Surveyor's funding was reduced. The launch date slipped. Fiscal year 2023 brought more cuts. The Biden administration's budget request allocated significantly less money to NEO Surveyor than the project needed to stay on schedule. The mission's cost estimate began to climb as the timeline stretched out. Delayed programs always cost more because you're paying salaries and overhead for a longer period without making proportional progress. The launch date slipped further. By late 22, NASA was projecting a June 28 launch date with a total development cost of $1.2 billion. Initial estimates from the early 2010s had put NEOCAM in the $500 to $600 million range. The cost had doubled, not because the telescope got more expensive, the design hadn't changed fundamentally, but because every year of delay adds costs while delivering no additional capability. Amy Mainzer, the mission's principal investigator from the University of Arizona, has been publicly frustrated about the delays. In statements to Space Policy Online, she explained, NASA's decision to slow down the funding in FY22 and 23 due to cost overruns in other missions has resulted in a delayed launch date, which pushes up the cost for NEO Surveyor but has nothing to do with the project itself. It would cost less if we were able to launch sooner. Think about that for a moment. The telescope is ready to build. The team is ready. The technology works. But budget cuts caused by unrelated programs forced NEO Surveyor to slow down, which made it more expensive, which made it easier to justify further delays. It's a vicious cycle, Congress noticed. Representative Frank Lucas, chairman of the House Science, Space and Technology Committee, sent a letter to NASA in 2022 expressing frustration with the delays. His committee's spokesperson issued a statement. NASA's decision to postpone the launch of the NEO Surveyor to 2028 is unacceptable. Congress has been explicit that NEO Surveyor must launch by March of 2026. This is, in fact, the only program NASA is obligated to complete by law, so this delay is particularly troubling. NASA has already failed to meet its 2020 deadline to identify 90% of near-Earth objects larger than 140 meters. Yet the Biden administration cut the program funding this year and are now delaying it further, a move which will only add to the total mission cost. Let me repeat that. This is the only program NASA is obligated to complete by law. There's no legal requirement that NASA send astronauts to Mars. There's no law demanding a mission to Europa or Enceladus. There's no congressional mandate for the James Webb Space Telescope or the Roman Space Telescope, or any of a dozen other flagship missions. Those are important, valuable programs that expand human knowledge and inspire the public. But they're not legally required. NEO Surveyor is legally required. It's the only way to fulfill the 2005 mandate, and it keeps getting pushed back. In 2024 and early 2025, the mission managed to make progress, despite the constrained budget. NASA conducted the Key Decision Point C review in September 2024, a critical milestone where the agency evaluates whether a mission is ready to move from design into full-scale construction. NEO Surveyor passed. Construction on the telescope's hardware began. The team, led by NASA's Jet Propulsion Laboratory in Pasadena, California, started fabricating the actual flight components. By May 2025, when Amy Mainzer testified before a House subcommittee, the mission was actually ahead of the delayed schedule. She projected a late 2027 launch, several months earlier than the 2028 commitment NASA had made to Congress. Good news finally, but let's put this in context. The 2005 mandate set a 2020 deadline for cataloguing 90% of hazardous asteroids. It's now 2025, and we're 5 years overdue. The telescope that could finally complete this task won't launch until late 2027 at the earliest. Once in space, NEO Surveyor will need 10 to 12 years to survey enough of the sky to reach that 90% threshold. That means we're looking at the late 2030s before the congressional mandate is fulfilled, roughly 15 years late and 3 decades after the law was passed. Without NEO Surveyor, using only ground-based telescopes, NASA estimates it would take at least 30 years from now to reach 90% sometime in the 2050s. Ground-based surveys simply cannot observe the regions near the Sun where many hazardous asteroids hide. You need a space-based infrared telescope positioned where it can see those regions. There's no alternative. And here's what makes this even more frustrating. NEO Surveyor isn't some pie-in-the-sky experimental technology. It's based on proven systems. The infrared detectors are similar to those used on the WISE and NEO-WISE missions, which successfully surveyed the sky for years. The orbital mechanics of placing a telescope at L1 are well understood. We've put spacecraft there before. The NEO Surveyor team isn't inventing new physics. They're applying mature technology to solve a specific, well-defined problem. The L1 Lagrange point is about 1.5 million kilometers from Earth, roughly 4 times the distance to the Moon, positioned along the line between Earth and the Sun. It's gravitationally balanced, so spacecraft there orbit the Sun in sync with Earth, remaining at a fixed distance from our planet. This makes communications easy. You're always pointing the same direction to talk to the spacecraft. And critically, from L1, you can observe the sky near the Sun without Earth or the Moon getting in the way. NEO Surveyor's telescope will be about 50 centimeters in diameter, modest by astronomical standards, but large enough to detect asteroids hundreds of meters across at distances of millions of kilometers. It will observe in 2 infrared bands around 5 to 10 micrometers wavelength. At these wavelengths, asteroids glow with their own thermal emission, heat radiated from their sun-warmed surfaces. This thermal emission isn't drowned out by sunlight the way reflected visible light is. An asteroid might be impossible to see in visible light when near the Sun, but in the infrared, it's a warm object against the cold background of space. It stands out. Earth's atmosphere blocks most infrared radiation at the wavelengths NEO Surveyor will use. That's why ground-based infrared surveys can't do this job, even if they could somehow. Observe near the Sun, you need to be in space, above the atmosphere. NEO Surveyor will scan the entire sky every 2 weeks. Over the course of months and years, it will build up a comprehensive catalogue of objects, tracking their motion, measuring their sizes, characterizing their orbits. Asteroids that cross Earth's orbit will be identified. Their future trajectories will be calculated. If one is on a collision course with Earth decades in the future, we'll know, and that knowledge is everything. Because we now have the ability to deflect asteroids. We've tested it, but deflection only works if you have warning time. If an asteroid is detected a few days before impact, like the Chelyabinsk meteor, there's nothing you can do except evacuate the impact zone and hope for the best. If it's detected decades in advance, you can launch a deflection mission and nudge it onto a safe trajectory. The difference between catastrophe and a footnote in history is early detection. NEO Surveyor provides early detection, but only if we launch it. The NASA Inspector General's Office has weighed in on this problem multiple times. In a 2021 report on NASA's planetary science portfolio, the OIG found that the Near-Earth Object Program had been consistently underfunded, and that delays to NEO Surveyor were putting the congressional mandate further out of reach. The report noted that without a dedicated space-based infrared mission, NASA would not be able to achieve the 90% cataloging goal in any reasonable timeframe. Let me give you some numbers to put this in perspective. NASA's total annual budget is around 25 to 27 billion depending on the year. The Planetary Science Division gets roughly 3 to 3.5 billion of that. NEO Surveyor's total development cost is estimated at $1.2 billion spread over multiple years. That's a large sum in absolute terms, but it's a small fraction of NASA's planetary science budget. It's roughly equivalent to the annual budget for a single flagship mission like the Europa Clipper or the Mars Sample Return Program. The difference is that NEO Surveyor is legally mandated and addresses an existential risk, while other missions, however scientifically valuable, are not required by law and do not directly protect human civilization from destruction. I'm not arguing we should cancel scientific exploration, but there's something deeply wrong when the one program Congress explicitly required NASA to complete keeps getting delayed while discretionary programs move forward. And the delays have real consequences. Every year without NEO Surveyor is another year where potentially hazardous asteroids remain undetected. Some of those asteroids are on trajectories that will bring them close to Earth in the 2030s, 2040s, or 2050s. If we find them soon, we have time to plan and execute deflection missions. If we don't find them until NEO Surveyor launches in late 2027 and completes its survey in the late 2030s, we might discover an asteroid that will impact Earth in the 2040s, giving us less than a decade to prepare. That's a tight timeline for designing, building, launching, and executing a deflection mission, especially if the asteroid is large and requires multiple impacts or a more complex deflection strategy. And if we find an asteroid even later, say one that NEO Surveyor detects in the early 2040s on a trajectory that impacts Earth in the early 2050s, the timeline becomes even more constrained. At some point you run out of time. You detect the asteroid, you know it's going to hit, and there's nothing you can do because you don't have enough years to mount an effective deflection campaign. This isn't hypothetical. We know for certain that there are asteroids in orbits that will bring them close to Earth in the coming decades. We know for certain that some of those asteroids are larger than 140 meters. And we know for certain that many of them are currently undetected because they spend much of their time in the sun's blind spot. The question isn't whether one of them might be on a collision course with Earth. The question is whether we'll find it in time to do anything about it. Let's talk numbers. How many asteroids are we actually missing? And how dangerous are they? The 2005 congressional mandate set the target at 140 meters because that's where impacts transition from local disasters to civilization-threatening events. But the threat spectrum is much wider than that. Asteroids come in a huge range of sizes, and the damage they cause scales dramatically with size. At the small end, we have objects like the Chelyabinsk meteor, 20 meters in diameter, about 13,000 metric tons, impacting with energy around 500 kilotons. That's enough to shatter windows across a city, injure thousands of people, and cause tens of millions of dollars in damage. Scary but not civilization ending. There are probably millions of 20-meter asteroids in near-Earth space. We've catalogued a tiny fraction of them. Most will never hit Earth, but statistically, impacts of this size happen every few decades. The Chelyabinsk event in 2013 was the first one to occur over a populated area in the modern era, but smaller asteroids have exploded over remote regions without making headlines. At 50 meters, you're talking about the Tunguska event, an asteroid that exploded over Siberia in 1908 with energy estimated at 3 to 5 megatons, flattening 2,100 square kilometers of forest. Had that explosion occurred over a city, it would have killed everyone within the devastation zone, potentially hundreds of thousands or millions of people, depending on population density. The Tunguska impactor was probably 50 to 60 meters across. Objects in this size range impact Earth roughly every few hundred years. We've catalogued almost none of them. There are probably hundreds of thousands of 50-meter near-Earth asteroids, and we found maybe a few thousand. At 140 meters, the congressional threshold, you're looking at a regional catastrophe. An impact would devastate an area the size of a small country or a large metropolitan region. If it struck land, millions of people could die from the direct effects: the blast, the heat, the seismic shaking. If it struck ocean near a coastline, the tsunami could kill tens of millions. This is the size where you start seriously disrupting global infrastructure and potentially triggering secondary disasters like economic collapse, refugee crises, and geopolitical instability. Objects in this size range hit Earth roughly every 20,000 to 30,000 years. Scientists estimate there are about 25,000 near-Earth asteroids of 140 meters or larger. We've found 40 to 44% of them. That leaves 14,000 to 15,000 undetected. At 300 meters, the devastation is continental. An impact creates a crater dozens of kilometers wide, triggers earthquakes across an entire region, and throws enough dust into the atmosphere to affect climate for years. Crop failures follow, famines spread, governments collapse. This is the size that threatens modern civilization. Objects in this range impact Earth roughly every 100,000 years. There are probably several thousand 300-meter near-Earth asteroids. We've found maybe half of them. At 1 kilometer, you're approaching global catastrophe. The famous dinosaur killer that struck 66 million years ago was about 10 kilometers across, but even a 1-kilometer asteroid would cause worldwide devastation. The impact itself would destroy everything within thousands of kilometers. The dust and debris ejected into the atmosphere would block sunlight for months, causing global crop failures, mass starvation, and likely the collapse of industrial civilization. Objects in this size range hit Earth every 500,000 to 1,000 years. Scientists estimate there are about 900 to 1,000 near-Earth asteroids of 1 kilometer or larger. We found more than 95% of them, which is good news. The bad news is that more than 95% isn't 100%. There are still a handful of kilometer-scale asteroids out there that we haven't found, and some of them are probably hiding in the sun's glare. Now let's focus on the 140-meter-plus population, because that's what the congressional mandate targets and what NEO surveyor is designed to find. 25,000 total estimated, 10,000 to 11,000 found, 14,000 to 15,000 missing. Where are those 14,000 to 15,000 asteroids? Some of them are in orbits that keep them far from Earth most of the time, making them faint and hard to detect. Those will be found by ground-based surveys, eventually, as telescopes get bigger and more sensitive. Some of them are in the outer solar system, orbiting beyond Mars, only occasionally venturing into near-Earth space. Those too will be found by surveys scanning the entire sky, but a significant fraction, thousands of them, are in orbits that bring them close to the Sun. Some are Ateras, with orbits inside Earth's orbit. Some are ATENs, with orbits that cross Earth's orbit but stay mostly between Earth and the Sun. These asteroids spend a large portion of their time at small solar elongations in the blind spot. Ground-based surveys can only observe them during brief windows when they reach maximum elongation, and even then, only during twilight. Most of the time, they're invisible. Scott Shepherd's twilight surveys have found a few dozen of these objects over the past decade. That's an impressive achievement given the difficulty of the observations, but it's a tiny fraction of what's out there. For every Atera or ATEN that Shepherd finds, there are probably dozens or hundreds that remain undetected. The searchable volume of space is simply too large, and the observing windows are too brief for ground-based surveys to comprehensively map the population. And remember, you don't need an asteroid to be an Atera or ATEN for it to approach Earth from the direction of the Sun. Any asteroid on any trajectory can have a close approach geometry where it's sunward as seen from Earth. The asteroid 2023 NT1, which passed within 3,600 kilometers of Earth and wasn't detected until 2 days after closest approach, wasn't an Atera. It was just approaching from an unfortunate direction. This happens regularly. In January 2023, the asteroid 223 passed within 2,200 miles of Earth's surface, closer than geosynchronous satellites orbit. It's about 4 to 8 meters across, so not a civilization ender, but still large enough to cause localized damage if it had hit. It was detected only a few days before closest approach. Again, sunward approach geometry. This pattern keeps repeating. Asteroids making close approaches to Earth, detected late or not at all, because they're coming from the direction of the Sun. And while many of these are small objects that wouldn't cause catastrophic damage, the existence of 2025 has 79, a 700-meter beast hiding in twilight, proves that large objects are also lurking in the blind spot. How dangerous is a 700-meter asteroid? Let's do the math. An asteroid's kinetic energy depends on its mass and velocity. Mass scales with volume, which scales with the cube of diameter. A 700-meter asteroid has a volume about 120,000 times larger than the 20-meter Chelyabinsk meteor. If they have similar densities and impact velocities, the 700-meter object would carry about 1.37 million times more kinetic energy. The Chelyabinsk meteor released 500 kilotons. Multiply by 1.37 million, and you get 685 billion kilotons, or 685,000 megatons. That's a rough estimate because impact velocity matters a lot and can vary significantly depending on the asteroid's orbit. A slow, grazing impact delivers less energy than a fast, head-on collision. But even being conservative, a 700-meter asteroid impacting at typical near-Earth asteroid velocities would release energy on the order of 100,000 to 1,000,000 megatons. For comparison, the largest nuclear weapon ever detonated, the Soviet Tsar bomber in 1961, was 50 megatons. A 700-meter asteroid impact would be thousands of times more powerful than the largest nuclear bomb ever built. An impact of that scale would create a crater dozens of kilometers wide. If it hit land, it would destroy everything within a radius of hundreds of kilometers. The blast wave would level cities. The seismic shaking would trigger earthquakes. The heat would ignite fires across an entire region. If it hit ocean, the tsunami would propagate across the entire ocean basin, inundating coastlines thousands of kilometers away, with waves tens of meters high. The death toll would be in the hundreds of millions, potentially billions, depending on where it struck and how many secondary disasters followed. This is not a regional disaster. This is a continental-scale catastrophe, possibly a civilization-threatening event if it hit the right location, say, the eastern seaboard of the United States, Western Europe, or East Asia. Any of those impacts would destroy trillions of dollars of infrastructure, kill tens to hundreds of millions of people immediately, and trigger global economic collapse. And 2025 SC79 An object exactly this dangerous was completely unknown until September 2725. It had been hiding in the sun's glare, invisible to our detection systems, for as long as it's been in its current orbit. We only found it because Scott Shepherd happened to be conducting a twilight survey at the right time, looking at the right patch of sky with one of the few telescopes capable of this kind of observation. How many others are still hiding? We don't know. By definition, we can't count what we can't see, but based on population models and discovery rates, astronomers estimate that thousands of asteroids larger than 140 meters remain undetected in near-Sun orbits. Some of those are certainly in the 300-meter plus range. Some might be 500 meters. Some might be even larger. And it's not just the Ateras we should worry about. Our 10 asteroids, which have orbits that cross Earth's orbit but stay mostly inside it, are also systematically underrepresented in our catalogues. The 2013 Chelyabinsk meteor, interestingly, was on an Apollo-type orbit that brought it from the direction of the Sun, but didn't keep it inside Earth's orbit permanently. The key factor wasn't the orbital classification, it was the geometry of approach. The asteroid was sunward, so we couldn't see it. The same thing can happen with larger objects. An asteroid on a perfectly conventional Earth-crossing orbit, one that spends most of its time outside Earth's orbit and should be easy to detect, can still surprise us if its close approach happens to occur when it's positioned between Earth and the Sun. In that configuration, even if the asteroid is on a trajectory that will eventually cause an impact, we might not detect it until shortly before collision. This is the nightmare scenario: a large asteroid, 140 meters or bigger, approaching Earth on a collision trajectory. Invisible because it's in the Sun's glare, detected too late for deflection. It's not a hypothetical, it's a real gap in our detection capabilities. And it remains a gap until we get a space-based infrared telescope positioned to observe near the Sun. Let's compare this threat to 3IATLAS, the interstellar comet everyone's talking about. 3IATLAS was discovered in July 2012, when it was still outside Mars' orbit, roughly 200 million kilometers from Earth. It approached the Sun in October 2025, reaching perihelion, closest point to the Sun, at a distance of about 39 million kilometers. That's inside Mercury's orbit, but still far from Earth. At closest approach to Earth, 3IATLAS will be about 26 million miles, 203 million kilometers away. That's farther than the distance from Earth to the Sun. 3IATLAS is on a hyperbolic trajectory. It's moving fast enough to escape the Sun's gravity, which means it will pass through the inner solar system once and never return. We've tracked it continuously since discovery. We know exactly where it is, where it's going, and when it will leave. Its orbit has been calculated with high precision based on months of observations. There is zero chance it will hit Earth. Zero. So why is 3IATLAS getting so much attention? Because it's probably an interstellar object, only the third confirmed visitor from outside our solar system, after Oumuamua in 2017 and Comet Borisov in 2019. It's scientifically fascinating. Avi Loeb and others are speculating about its origins, whether it might be a natural comet or something more exotic. Observations suggest it may be fragmenting as it moves away from the Sun, which raises questions about its composition and structure. All of that is interesting. I'm not dismissing the scientific value of studying 3IATLAS. But here's the thing. 3IATLAS poses zero threat to Earth. It's far away, fully tracked, and leaving the solar system. Meanwhile, we have thousands of undetected asteroids in near-Earth orbits, some of them crossing Earth's path, some of them large enough to devastate continents, and we don't know where they are. The media is breathlessly covering a distant, harmless interstellar visitor, while ignoring a far more immediate threat right in our cosmic backyard. Let me be clear, I'm not saying scientists shouldn't study 3IATLAS, but the allocation of public attention is completely backward. A distant, harmless object that will never threaten Earth gets headlines and breathless speculation, while thousands of undetected asteroids in near-Earth orbits, some capable of destroying civilizations, remain in the shadows, literally and figuratively. The sun's blind spot is hiding the real threat, and we're looking the wrong way. And the most frustrating part, we have proven tested technology to deflect asteroids if we find them in time. We're not helpless, we just need to see what's coming. September 26, 2022, a moment that should have received far more attention than it did. NASA's Double Asteroid Redirection Tests spacecraft, DART, deliberately crashed into an asteroid called Dimorphos at 23:14 UTC. This wasn't an accident. This wasn't a close approach or a flyby. This was a kinetic impactor mission, a spacecraft designed to slam into an asteroid at high speed and change its trajectory. A test of humanity's ability to deflect an asteroid that might someday threaten Earth. DART was traveling at about 6.6 kilometers per second when it hit Dimorphos. The spacecraft itself weighed about 570 kilograms, roughly the size of a small car. Dimorphos, the target asteroid, is about 160 meters in diameter, roughly the size of a large building. The collision occurred about 11 million kilometers from Earth, roughly 29 times the distance to the Moon. The goal was to change Dimorphos's orbit around its companion asteroid, Didymos. Dimorphos is actually a moon of the larger asteroid, orbiting Didymos every 11.92 hours before the impact. Scientists predicted that DART's impact would shorten that orbital period by at least 73 seconds. That was the success threshold. If the orbital period changed by more than 73 seconds, the mission would be considered successful. The actual result exceeded all expectations. In the days and weeks following the impact, astronomers around the world used ground-based telescopes to measure how much Dimorphos's orbit had changed. They observed the system as Dimorphos passed in front of Didymos, blocking some of its light, a mini eclipse that happens regularly in binary asteroid systems. By timing these eclipses before and after the DART impact, they could measure the change in orbital period with extreme precision. The result, Dimorphos's orbital period decreased by 32 minutes. Not 73 seconds, 32 minutes. That's about 26 times larger than the minimum success threshold. The impact was extraordinarily effective. Why did it work so well? The answer lies in what happened to all the material that got ejected when DART hit. The spacecraft itself transferred momentum to Dimorphos through the direct impact. Basic Newtonian physics, conservation of momentum. But the collision also excavated a huge amount of material from Dimorphos's surface. That debris was ejected at high speed, and by Newton's third law, every action has an equal and opposite reaction. The ejection of debris created a rocket-like thrust that pushed Dimorphos in the opposite direction. This momentum enhancement effect turned out to be much larger than the direct impact effect. Substantially more momentum was transferred to Dimorphos from the escaping impact ejector than from the spacecraft itself. The impact created a plume of debris that acted like a rocket exhaust, amplifying the deflection. Scientists had predicted this might happen, but they didn't know how large the effect would be. It depends on the asteroid's composition, surface properties, internal structure, all things that are hard to measure remotely. DART provided the first real-world test of kinetic impact deflection, and the results were better than hoped. The implications are profound. We now have direct experimental evidence that kinetic impactors can deflect asteroids. This isn't theoretical anymore. We've done it. We know the technique works, and we know it works better than our conservative models predicted. Here's what that means for planetary defense. If we detect a hazardous asteroid decades before it's predicted to impact Earth, we can launch a DART-like mission, hit the asteroid, change its velocity by a small amount, and over the course of years or decades, that small velocity change accumulates into a large change in position. The asteroid that would have hit Earth misses by thousands or millions of kilometers instead. The key word in that sentence is decades. Deflection only works if you have enough warning time. Let me give you the numbers. When DART hit Dimorphos, it changed the asteroid's velocity by about 3 millimeters per second. That's tiny, roughly walking speed. But Dimorphos is 160 meters across, similar in size to the asteroids the congressional mandate targets. If you changed a 160-meter asteroid's velocity by 3 millimeters per second when it was, say, 20 years away from a predicted Earth impact, how much would its position change by the time it reached Earth? The asteroid is traveling roughly 20 to 30 kilometers per second in its orbit, typical for near-Earth asteroids. A velocity change of 3 millimeters per second is tiny compared to that, but it accumulates over time. After 1 year, the asteroid would be displaced by about 95 kilometers from where it would have been. After 10 years, about 950 kilometers. After 20 years, about 1,900 kilometers. Earth's diameter is about 12,700 kilometers. If you can shift an asteroid's trajectory by 1,900 kilometers over 20 years, you can turn a direct hit into a clean miss. You don't need to blow up the asteroid or vaporize it. You just need to nudge it slightly so that by the time it reaches Earth's orbit, we're not there anymore. And the earlier you apply the deflection, the better. The same velocity change applied 50 years before impact would shift the asteroid's position by nearly 5,000 kilometers. Applied 100 years before impact, about 9,500 kilometers. The deflection required gets smaller and smaller the more warning time you have. This is why early detection is everything. With decades of warning, deflecting a hazardous asteroid is straightforward. Launch a spacecraft, hit the asteroid, measure the orbit change, and if needed, launch a second mission to fine-tune the deflection. With a few years of warning, it's much harder because you need a bigger deflection, which might require multiple impacts or more advanced techniques like gravitational tractors or nuclear standoff explosions. With a few months of warning, there's nothing you can realistically do except evacuate the impact zone and hope it doesn't hit anything critical. And with a few days of warning, like the Chelyabinsk meteor, you can't even evacuate effectively because you don't know precisely where it will hit. You know it's coming, but atmospheric effects during entry are unpredictable. The entry angle, the fragmentation behavior, the final impact point, all uncertain until the last moments. All you can do is tell people to stay away from windows and hope the casualty count stays low. This is the nightmare, a large asteroid approaching Earth from the sun's direction, detected too late for deflection, on a trajectory that will cause a regional or continental catastrophe. We have the technology to prevent this. DART proved it. But we can't use that technology if we don't see the asteroid in time. The DART mission cost about $330 million. That's a lot of money in absolute terms, but it's a tiny fraction of what a major asteroid impact would cost in economic damage, not to mention the human casualties. The Chelyabinsk meteor, a 20-meter object, caused $33 million in damage. A 140-meter asteroid would cause trillions of dollars in damage. Spending hundreds of millions on planetary defense missions is a bargain compared to the alternative. And here's the thing, we only need to deflect an asteroid once every few thousand years at most. The probability of a civilization-threatening impact in any given year is very low. But over centuries and millennia, it's not a matter of if, but when. Eventually, if we don't have an effective detection and deflection system, a large asteroid will hit Earth. It's inevitable. The only question is whether we'll see it coming and do something about it, or whether we'll be caught by surprise. Right now, we're on track for the caught by surprise scenario, at least for asteroids hiding in the sun's glare. We've proven we can deflect them. We've designed the telescope that can find them, and we're delaying its launch over budget concerns that pale in comparison to the cost of a major impact. The European Space Agency is also working on this problem. In June 2025, ESA announced its NEOMER mission concept. NEOMER, Near-Earth Object Mission, in the infrared, would be a small infrared telescope positioned at the L1 Lagrange point, similar to NEO Surveyor, but with a different observing strategy. While NEO Surveyor will scan the entire sky every 2 weeks, building up a comprehensive catalogue of asteroids over years, NEOMER is designed as an early warning system. It would scan a ring around the Sun every 6 hours, looking specifically for asteroids that are currently approaching Earth from sunward directions. If an asteroid is detected, NEOMER would provide immediate alerts so that follow-up observations could characterize its orbit and determine if it's a threat. The two missions are complementary. NEO Surveyor provides the long-term, comprehensive survey that fulfills the congressional mandate. NEOMER provides short-term warning of imminent threats. Together, they would close the blind spot almost completely. Even objects like the Chelyabinsk meteor, which are too small for NEO Surveyor to detect at long range, would be caught by NEOMER in the final weeks or days before a potential impact. ESA projects NEOMER could detect objects as small as 20 meters in diameter, with at least 3 weeks of warning. That's not enough time for deflection, but it's enough time to evacuate impact zones, prepare emergency services, and minimize casualties. For larger objects, 140 meters and up, NEOMER could provide months to years of warning, depending on when they enter its surveillance zone. NEOMER is currently in the study phase. ESA hasn't committed to a launch date yet, but the mission concept is being seriously evaluated as part of the agency's space safety program. If funded, it could launch in the early 2030s. So the good news is that the technology exists to solve the blind spot problem. NEO Surveyor and NEOMER, working together, could detect nearly all hazardous asteroids, even those hiding in the sun's glare. Combined with dark-proven deflection techniques, humanity would have a real planetary defense system. The bad news is that we're not building these systems fast enough. NEO Surveyor won't launch until late 2027 at the earliest, and won't complete its survey until the late 2030s. NEOMER is still in the planning stages. Meanwhile, the blind spot remains wide open, and thousands of potentially hazardous asteroids remain undetected. Every year of delay is another year of vulnerability. And unlike most other risks we face, pandemics, climate change, nuclear war, asteroid impacts are entirely preventable if we put in the effort. We don't need to change human behavior or negotiate international treaties or develop new physics. We just need to build the telescopes, launch them, and use the data to guide deflection missions when needed. It's a solvable problem. The fact that we're not solving it faster is a failure of priorities, not a failure of capability. Let's get into the technical details of how NEO Surveyor will actually work, because understanding the engineering makes it clear just how essential this mission is, and how frustrating the delays have been. NEO Surveyor is a space-based infrared telescope designed specifically for asteroid detection. It will operate at the L1 Lagrange point, about 1.5 million kilometers from Earth, positioned along the line between Earth and the Sun. This location is gravitationally stable. The combined gravitational pulls of Earth and the Sun, plus the centrifugal force from orbiting the Sun, balance out, allowing spacecraft to remain at L1 with minimal fuel expenditure. From L1, NEO Surveyor will have an unobstructed view of the inner solar system. It will be able to observe regions of space that are too close to the Sun for ground-based telescopes to see. And critically, it will observe in infrared wavelengths, where asteroids glow with thermal emission rather than reflected sunlight. Here's why infrared is essential. When you look at an asteroid in visible light, you're seeing sunlight bouncing off its surface. The asteroid is only visible because the Sun is illuminating it. If the asteroid is positioned between Earth and the Sun, in the blind spot, it's backlit. From our perspective, we're looking at its dark side, and the bright glare of the sun drowns out what little reflected light might reach us. This is why ground-based surveys struggle with twilight asteroids. But asteroids aren't just reflective objects. They're also thermal objects. When sunlight hits an asteroid's surface, it heats the rock to temperatures of 200 to 400 Kelvin, sometimes higher for objects close to the sun. At these temperatures, asteroids emit infrared radiation, heat, in wavelengths around 5 to 20 micrometers. This thermal emission doesn't depend on reflected sunlight. The asteroid glows in the infrared simply because it's warm. From an infrared telescope's perspective, an asteroid near the sun is a warm object against the cold background of space. It stands out clearly, even if it's geometrically positioned between the telescope and the sun. You're not looking for reflected light, you're looking for the asteroid's own thermal glow. This is the fundamental advantage of infrared asteroid detection. It works regardless of the sun's position. An asteroid that's invisible light because of the sun's glare, is still perfectly visible in infrared because of its thermal emission. NEO Surveyor's telescope will be about 50 centimeters in diameter, modest compared to astronomical giants like Hubble or JWST, but perfectly adequate for asteroid detection. The telescope doesn't need to resolve fine details or study distant galaxies. It just needs to detect point sources, asteroids, moving against the background stars. The telescope will carry 2 infrared detector arrays, observing in 2 wavelength bands, approximately 4 to 5 micrometers and 6 to 10 micrometers. These bands are chosen to maximize asteroid detection while minimizing interference from zodiacal light, the faint glow of sunlight scattered by interplanetary dust. By observing in multiple wavelengths, NEO Surveyor can also characterize asteroid properties like size and reflectivity. Determining an asteroid's size is surprisingly tricky. If you observe an asteroid in visible light, you're measuring how much sunlight it reflects. But that depends on both its size and its albedo, surface reflectivity. A small bright asteroid might reflect the same amount of light as a large dark asteroid. Without additional information, you can't tell them apart. Infrared observations break this degeneracy. Thermal emission depends primarily on the asteroid's temperature and surface area. Temperature is determined by distance from the sun and spin rate, both of which can be estimated or measured. Surface area is directly related to size. By combining visible light and infrared observations, you can solve for both size and albedo independently. This matters because hazard assessment depends on size. A 50-meter asteroid hitting Earth is a local catastrophe. A 500-meter asteroid is a continental disaster. You need to know which you're dealing with. NEO Surveyor's observing strategy is elegantly simple. The telescope will scan the sky in a systematic pattern, covering the entire accessible sky, about 85% of the celestial sphere, every 2 weeks. Each region of sky is observed multiple times during each scan to detect moving objects and measure their motion against background stars. When the telescope detects a moving object, ground-based follow-up observations confirm it's an asteroid and refine its orbit. Over weeks and months, repeated observations from NEO Surveyor and ground-based telescopes build up a precise orbital solution. Within a year or 2 of discovery, most asteroids will have well-determined orbits that allow predictions decades or centuries into the future. The mission is designed to operate for at least 5 years, with a goal of 10 to 12 years. Over that time, NEO Surveyor will discover an estimated 200,000 to 300,000 near-Earth objects. Most of these will be small, below the 140-meter congressional threshold, but they'll still be valuable to catalogue. The mission will also discover tens of thousands of 140-meter-plus asteroids, bringing the total detection rate for that size class from the current 40% up to 90% or more. Critically, NEO Surveyor will be able to detect Atira and Vatira asteroids, the population hiding inside Earth's orbit that ground-based surveys mostly miss. Current estimates suggest there are hundreds of Asteroids and Apophis larger than 140 meters. We've found a few dozen. NEO Surveyor will find the rest. The spacecraft design is relatively straightforward. The telescope and instruments are cooled passively using a large sunshield, similar in concept to a GUST sunshield, but smaller. The detectors need to be cold, around 40 Kelvin, to reduce their own thermal emission, which would otherwise interfere with detecting faint asteroids. A combination of radiators and heat rejection systems keeps everything at the right temperature. Power comes from solar panels that deploy after launch. Communications use NASA's Deep Space Network, the same ground-based antenna array that communicates with spacecraft throughout the solar system. Data is downlinked regularly, images, telemetry, spacecraft health information, and processed on the ground by automated pipelines that identify moving objects and calculate preliminary orbits. The whole system is designed to be reliable and low maintenance. Once NEO Surveyor reaches L1 and begins operations, it should be able to run for years with minimal intervention. The mission doesn't require complex maneuvers or risky operations. It's a survey mission. Point, scan, detect, repeat. From an engineering perspective, NEO Surveyor is actually less challenging than many other space missions. It's not landing on another world like Perseverance, Curiosity. It's not performing close flybys of asteroids like OSIRIS-REx. It's not observing the earliest galaxies in the universe like JWST. It's a relatively simple infrared survey telescope designed to do one job very well: find asteroids. And yet, despite being the only mission NASA is legally mandated to complete, it has been delayed repeatedly. The development timeline looks something like this. Early 2010s. NEOCAM proposed to NASA Discovery Program multiple times. Highly rated, but not selected for full funding. 2019. Elevated from Discovery Program to standalone planetary defense mission. Renamed NEO Surveyor. Baseline launch date in mid-2020s. 2021. Development begins. Preliminary design review completed successfully. 2022. Budget cuts due to cost overruns on other missions. Funding reduced. Launch date slips to 2026. 2023. Further budget constraints. Launch date slips to June 2028. Cost estimate rises to $1.2 billion 2024. Key decision. Point C review completed successfully. Construction begins, still targeting June 2028. Launch 2025. Mission ahead of internal schedule. Principal investigator Amy Mainzer projects possible late 2027 launch. So the current best estimate is late 2027 or early 2028. With operations beginning shortly after arrival at L1. That's about 3 months for transit and commissioning. So science operations would start in early 28. Once operational, NEO Surveyor will begin its systematic survey. Over the next 10 to 12 years, it will build up a comprehensive catalogue of near-Earth asteroids, finally fulfilling the congressional mandate that was supposed to be completed by 2020. Better late than never, but the delays matter. Every year without NEO Surveyor is a year where the blind spot remains open. Asteroids continue to approach Earth from sunward directions, undetected. Some of them might be on trajectories that will bring them dangerously close in the 2030s or 2040s. If we find them in 2028 with NEO Surveyor, we have time to plan deflection missions. If we don't find them until they're detected by chance during a close approach, like 223 NT1, we might not have time. And here's a sobering thought. 225 S79, the 700-meter asteroid Scott Shepherd discovered in September, had been there all along. It's been orbiting the Sun for millions of years. It was there in 2005 when Congress passed the mandate. It was there in 2020 when we missed the deadline. It was there in 2005 when we're still waiting for NEO Surveyor to launch. We just didn't know it existed. How many others are still waiting to be discovered? Objects even larger than 2025 S79, hiding in the same blind spot, orbiting silently until one day their trajectory intersects Earth's at the wrong moment. We won't know until NEO Surveyor launches and completes its survey. And even then, there's always a chance of something slipping through, an asteroid on a highly unusual orbit, or a long-period comet from the outer solar system making its first pass through the inner solar system. No detection system is perfect, but NEO Surveyor would close the largest known gap in our planetary defense system. It would find the Atiras and Vatiras. It would detect asteroids approaching from sunward directions. It would characterize the orbits of tens of thousands of objects, allowing predictions decades or centuries into the future. Combined with DART-proven deflection techniques, it would give humanity the tools to prevent asteroid impacts that would otherwise cause catastrophic damage. The technology exists. The mission is being built. We just need to finish it and launch it. And in an ideal world, Neomir would launch a few years later, providing complementary coverage and early warning capabilities. Together, NEO Surveyor and Neomir would create a comprehensive planetary defense system that could detect virtually any asteroid threat with enough warning time to do something about it. The only obstacle is political will and funding. And given that we're talking about potentially preventing civilization-ending disasters, the cost seems remarkably small. NEO Surveyor's $1.2 billion development cost, spread over a decade, is less than what many countries spend on military equipment in a single year. The United States alone spends over $800 billion annually on defense. Spending a fraction of that to defend against asteroid impacts seems like an obvious investment. But government budgets are complicated, and priorities shift based on political pressures and public attention. Right now, planetary defense gets relatively little attention compared to other space initiatives. There's more excitement about Mars missions and lunar bases and searching for life on Europa than there is about cataloguing asteroids. And that's understandable. Exploration and discovery capture the imagination in ways that systematic surveys don't. But here's the thing. All those exciting missions assume civilization continues to exist. If a 700-meter asteroid slams into Earth tomorrow, there won't be Mars bases or Europa landers. There might not be a functioning space program at all, depending on where the impact occurs and how much damage it causes. Planetary defense isn't glamorous. It's not going to inspire movies or generate breathless headlines, unless we fail, in which case the headlines will be apocalyptic. But it's foundational. It's the insurance policy that allows all other long-term planning to make sense. And we're so close to having that insurance policy in place. NEO Surveyor is being built right now. The telescope components are being fabricated, the instruments are being assembled, the software is being written. In 2 or 3 years, if all goes according to the current schedule, it will launch to L1 and begin operations. After that, it's just a matter of time. The systematic survey will proceed, asteroids will be discovered and catalogued, and year by year, the blind spot will shrink. By the mid-2030s, we'll have found most of the large asteroids hiding in the sun's glare. By the late 2030s, we'll have reached the 90% threshold for 140-meter-plus objects. And from that point forward, Earth will be protected by a comprehensive detection system that can provide decades of warning for any potential impact. Unless something delays NEO Surveyor again, unless budget cuts force another slip in the schedule, or technical problems emerge during integration and testing, or launch vehicle availability becomes an issue. These are real risks. Space missions are complex and delays happen for all sorts of reasons. The current schedule assumes everything goes smoothly from here forward. History suggests that's optimistic. But assuming NEO Surveyor does launch in late 2027 or early 2028, and assuming it operates successfully for its planned lifetime, we'll finally have the capability to close the blind spot. And that's when Earth's planetary defense system will truly become operational. Let's talk about consequences. What actually happens if NEO Surveyor is delayed another 5 years? Or if it launches on schedule but Congress doesn't fund follow-up missions when hazardous asteroids are discovered? Or if we just continue muddling along with ground-based surveys and accept that large parts of near-Earth space will remain unsurveyed? The answer depends on luck, and humanity has been extraordinarily lucky so far. The last major asteroid impact on Earth occurred in 1908, the Tunguska event. An object estimated at 50 to 100 meters in diameter exploded over Siberia with energy around 3 to 5 megatons. It flattened 200 square kilometers of forest. Every tree within a radius of about 25 kilometers was knocked down, radiating outward from the epicenter. If you'd been standing in that forest, you would have seen a fireball approaching from the sky, heard a deafening roar, and then been hit by a blast wave traveling faster than the speed of sound. Death would have been instantaneous for anyone within tens of kilometers. But here's the key detail. It happened over one of the most remote, sparsely populated regions on Earth. Central Siberia in 1908 was wilderness. There were no cities nearby, no major infrastructure, no dense populations. The closest significant settlement was the town of Vanavara, about 65 kilometers from the explosion. Residents there reported seeing a bright flash and feeling intense heat, followed by a shockwave that blew out windows and knocked people off their feet. But casualties were minimal, possibly 0 human deaths, though reindeer herds were decimated. If that same asteroid had exploded over Moscow, St. Petersburg, London, Paris, New York, or any major city, millions of people would have died. The entire city centre would have been obliterated. Buildings flattened, fires ignited across hundreds of square kilometres, infrastructure destroyed. The economic and human cost would have been staggering. Governments would have fallen. The course of 20th century history would have been completely different. We got lucky. The asteroid hit empty forest instead of a metropolis. In 2013, the Chelyabinsk meteor was also lucky. In a perverse way, yes, it injured 1,500 people and caused tens of millions in damage, but it could have been so much worse. The meteor exploded at 23.3 kilometers altitude. If it had been on a slightly steeper entry angle, it might have exploded lower, delivering more of its energy to the ground. If it had been composed of stronger material that didn't fragment as easily, it might have reached the surface intact and created a crater in the middle of Chelyabinsk, killing thousands. And Chelyabinsk is not a huge city by global standards, population around 1.1 million. If the same meteor had exploded over Tokyo, Mumbai, Sao Paulo, or New York, the casualties would have been far higher simply due to population density. Again, we got lucky, but luck runs out. Over long enough timescales, asteroids do hit populated areas. We just haven't experienced it in the modern era, because the modern era of dense urban populations has only existed for about 150 years, a blink of an eye in cosmic terms. If we go back further in history, there's evidence of impacts that cause significant localized destruction, though not at the civilization-threatening level. The problem is that before modern record-keeping and scientific investigation, most impacts wouldn't have left clear historical records unless they occurred near major population centers. And over geological timescales, Earth has been hit repeatedly by large asteroids. The Chicxulub impact 66 million years ago, the one that killed the dinosaurs, was a 10-kilometer asteroid. That's a global catastrophe, mass extinction level. But there have been many smaller impacts in the millions of years since then, in the 100-meter to 1-kilometer range, that would have caused regional to continental devastation if they had occurred today. The statistical expectation is clear. It's not a question of whether Earth will be hit by a large asteroid, but when. And when could be next year, or it could be 10,000 years from now. The probabilities are low in any given year, but they're not zero. For a 140-meter asteroid, the congressional threshold, the estimated impact frequency is roughly once every 20,000 to 30,000 years. That sounds like a long time, but civilizations can persist for thousands of years. If human civilization continues for another 10,000 years, we'd expect to experience multiple impacts in this size range unless we actively prevent them. For a 1-kilometer asteroid, the civilization-threatening size, the impact frequency is roughly once every 500,000 to 1,000,000 years. Still rare, but not impossibly so. And remember, we've only catalogued about 95% of the 1-kilometer plus population. There are still dozens of unknown asteroids in this size class. What are the odds that one of them is on a trajectory that will impact Earth in the next century? Low, but not zero. And with 5% of the population undetected, some of those unknown asteroids might be hiding in the Sun's blind spot. Now let's consider the specific threat from asteroids like 2025 SC79. It's 700 meters across, large enough to cause continental-scale devastation. Its orbit keeps it mostly inside Earth's orbit, making it an Atera asteroid. These objects are systematically underrepresented in our catalogues because they're so hard to detect from Earth. How many 700-meter-plus Ateras are there? We don't know precisely because we haven't catalogued most of them. But based on population models, and the few we have found, astronomers estimate there are dozens to perhaps a couple hundred Ateras larger than 500 meters, and several hundred to over 1,000 in the 140-meter-plus range. Some of those orbits will cross Earth's orbit. Not all Ateras are completely interior to Earth's orbit. Some of them have elliptical orbits that bring them outside Earth's orbit at aphelion, their farthest point from the Sun, even if they stay inside at perihelion. Those are the ones that pose collision risks. Now, the phase space of possible orbits is huge, and Earth is a small target. Just because an asteroid's orbit crosses Earth's orbit doesn't mean the asteroid and Earth will ever be at the same place at the same time. Orbital dynamics are complex, and most Earth-crossing asteroids will never actually hit Earth. They'll miss by thousands or millions of kilometers every time their orbits intersect. But most isn't all. Over long timescales, thousands to millions of years, gravitational perturbations from the planet slowly change asteroid orbits. An asteroid that poses no threat today might drift into a dangerous orbit in 10,000 years, or it might drift out of a dangerous orbit into a safe one. The system is chaotic, and long-term predictions are impossible beyond a certain point because tiny uncertainties grow exponentially. What we can say with confidence is this: there are hundreds of undetected large asteroids in near-Sun orbits. Some of them cross Earth's orbit. Eventually, one of them will be on a collision trajectory with Earth. If we find it decades in advance, we can deflect it. If we don't find it until weeks or days before impact, we can't. And this is where the delays to NEO Surveyor become genuinely frightening. Every year without the mission is a year where those asteroids remain undetected. Some of them might be on trajectories that will bring them close to Earth in the 2030s or 2040s. If NEO Surveyor launches in 2027 and finds them in 2029 or 2030, there's time to plan and execute deflection missions. If the mission is delayed to 2032 and finds them in 2034 or 2035, the timeline becomes tighter. If there's another 5-year delay, beyond that we might not find certain asteroids until it's too late to deflect them. I'm not trying to be alarmist. The probability of a major impact in the next decade is genuinely low. But it's not zero, and the consequences of being wrong are catastrophic. We're gambling with civilization itself, and the most frustrating part is that this is an entirely preventable risk. We have the technology to find these asteroids. We have the technology to deflect them. We've tested both. The only thing preventing us from implementing a comprehensive planetary defense system is the decision to fund and launch the necessary missions. Consider the cost-benefit analysis. NEO Surveyor costs $1.2 billion, A 700-meter asteroid impacting a populated region would cause damage measured in trillions of dollars, not to mention millions of casualties. Even if the probability of such an impact in the next 50 years is only 0.1%, 1 in 1,000, the expected value of preventing it is in the billions. The mission pays for itself in purely economic terms, ignoring the incalculable value of the lives saved. And this isn't even accounting for the existential risk angle. A sufficiently large impact, say a 2-kilometer asteroid hitting a critical region, could trigger cascading failures that end modern civilization. Even if humanity survives, the loss of infrastructure, knowledge, and social organization could set us back centuries. The cost of that in human suffering and lost potential is beyond calculation. From a rational risk management perspective, investing in planetary defense is one of the most obvious decisions a civilization can make. The cost is modest, the technology exists, and the potential downside of not doing it is civilization ending. Yet we keep delaying. Why? Partly because the risk feels abstract. Asteroid impacts are rare enough that nobody currently alive has experienced a major one. The Tunguska event was over a century ago. Chelyabinsk was dramatic but not catastrophic. There's no visceral sense of threat the way there is with, say, pandemics or terrorism or climate change, things that affect people's lives on regular timescales, partly because space missions take a long time to plan and execute, and budget cycles are short. A politician advocating for NEO surveyor funding won't see the mission launch during their term in office, let alone see it discover hazardous asteroids and guide deflection missions. The benefits are decades away, while the costs are immediate. That creates a bias towards spending money on things with more visible short-term payoffs. And partly because planetary defense competes with other priorities, some of which are also important. Should we spend money on asteroid detection or climate research? On deflection missions or pandemic preparedness? On cataloguing asteroids or reducing global poverty? The answer, of course, is that we should do all of these things. The United States alone has a federal budget of over $6 trillion. The global economy is over $100 trillion. Finding $1.2 billion for NEO surveyor is a rounding error. We're not choosing between planetary defense and other priorities. We have more than enough resources to address multiple existential risks simultaneously. But government budgets don't work that way in practice. Money gets allocated based on political pressures, bureaucratic inertia, and what's captured public attention recently. Planetary defense doesn't generate headlines unless something goes wrong. So it gets deprioritized until perhaps the day when a large asteroid is detected on a collision course and there's not enough time to deflect it. Then, suddenly, everyone will care about planetary defense. There will be emergency funding, crash programs, heroic efforts to launch deflection missions on compressed timelines. Maybe it will work. Maybe the asteroid will be deflected at the last moment, and humanity will breathe a collective sigh of relief. Or maybe it won't work. Maybe the timeline will be too short, or the asteroid too large, or the deflection attempt will fail for technical reasons. And then a 700-meter asteroid will slam into Earth at 20 kilometers per second, releasing energy equivalent to thousands of nuclear weapons, and millions of people will die. In the aftermath, assuming civilization survives, there will be inquiries and investigations. Why didn't we detect the asteroid sooner? Why didn't we have a comprehensive survey system in place? Why did we keep delaying NEO surveyor despite knowing about the blind spot? And the answers will be frustratingly mundane. Budget constraints, competing priorities, bureaucratic delays, political inertia, nothing malicious, just a collective failure to treat a low probability, high consequence risk with the urgency it deserved. We have an opportunity, right now, to avoid that scenario. NEO surveyor is being built. It will launch in a few years if current plans hold. And once operational, It will close the blind spots and give us the comprehensive asteroid catalogue we need for effective planetary defense. But we're cutting it closer than we should. Every delay increases the risk that we'll discover a hazardous asteroid too late to do anything about it. Every year without NEO Surveyor is a year of unnecessary vulnerability. And the bitter irony is that we're obsessing over 3IATLAS, a distant, harmless interstellar visitor, while the real threat lurks in the sun's glare, undetected, potentially on a collision course. And we won't know until it's too late. So where do we go from here? What needs to happen to turn our half-functional planetary defense system into something that actually protects civilization? The immediate priority is ensuring NEO Surveyor launches on schedule and operates successfully. The mission is currently being built with a target launch date in late 2027 or early 2028. NASA and the Jet Propulsion Laboratory need to maintain focus, keep the project fully funded, and avoid further delays. This is the only program NASA is legally mandated to complete. It should be treated as mission critical, not as a discretionary program that can be pushed back whenever budgets get tight. Congress has an oversight role here. The House Science, Space and Technology Committee needs to keep pressure on NASA to meet the launch deadline. That means ensuring adequate funding in each fiscal year's budget, not cutting NEO Surveyor to cover overruns on other missions. When other programs go over budget, find savings elsewhere or request supplemental funding. Don't delay the one program that's required by law and addresses an existential risk. Once NEO Surveyor launches and begins operations, the survey will take 10 to 12 years to reach the 90% detection threshold for 140-meter-plus asteroids. During that time, thousands of new near-Earth objects will be discovered. Most will pose no threat, but some will be flagged as potentially hazardous, objects whose orbits pass close to Earth's orbit and might, under certain circumstances, collide with our planet. For each potentially hazardous object, follow-up observations will be needed to refine the orbit and calculate impact probabilities. Ground-based telescopes around the world already do this as part of existing planetary defense efforts, but the volume of new discoveries from NEO Surveyor will be unprecedented. Additional resources might be needed, more telescope time, more analysts, more computing power for orbit calculations. And if an asteroid is found to be on a collision trajectory with Earth, a deflection mission will need to be planned and executed. This is where DART's success becomes critical. We now know that kinetic impactors work. Future deflection missions can use similar designs, scaled appropriately for the target asteroid. But deflection missions need to be prepared in advance. You can't design, build and launch a spacecraft in a few months. Lead times are measured in years. That means when NEO Surveyor discovers a hazardous asteroid, there needs to be a standing mechanism for quickly initiating a deflection mission. Pre-approved budgets, spacecraft designs ready to adapt to specific targets, launch vehicles on standby. NASA is working on this. The agency's Planetary Defense Coordination Office, established in 2016, is responsible for coordinating efforts to detect and characterize near-Earth objects and planning response strategies, but the office is small and under-resourced compared to the scale of the problem. Here's what a mature planetary defense system would look like. Detection layer, NEO Surveyor and ground-based surveys continuously scan for near-Earth asteroids. ESA's NEOMIA provides complementary coverage and early warning. Between them, they detect and catalogue 95% plus of hazardous objects, with decades to centuries of warning time. Tracking layer, automated follow-up observations, refine orbits for newly discovered objects. Within weeks to months of discovery, precise orbital elements are calculated, allowing prediction of future close approaches and impact probabilities. Assessment layer, risk assessment. Teams evaluate potential threats. Objects with non-zero impact probabilities are prioritized for further study. Impact simulations are run to estimate damage if deflection fails. Evacuation and emergency response plans are developed for worst-case scenarios. Deflection layer. For objects on collision trajectories, deflection missions are initiated. Lead time should be 10 to 20 years minimum for best results, but even a few years can work for smaller asteroids. Multiple deflection techniques are available. Kinetic impactors like DART, gravitational tractors for very slow deflections, nuclear standoff explosions for worst-case scenarios. Verification layer. After deflection attempts, the asteroid's new orbit is carefully measured to confirm it no longer poses a threat. If needed, follow-up missions fine-tune the deflection. None of this is science fiction. All of these components either already exist or are in development. We just need to commit to building the full system and keeping it operational indefinitely. And indefinitely is the key word. Planetary defense isn't a one-time project. It's an ongoing responsibility. Asteroids continue to evolve their orbits due to gravitational perturbations. New objects enter near-Earth space from the main asteroid belt or from long-period comet orbits. A comprehensive catalogue today isn't comprehensive in 50 years. Surveys need to continue, tracking networks need to be maintained, deflection capabilities need to be tested and upgraded. This is similar to how we treat other ongoing threats: military defense, public health infrastructure, emergency response systems. You don't build an army, win a war, and then disband the army. You maintain it because new threats can emerge. Similarly, you don't detect 90% of asteroids and then shut down the survey program. You keep observing because new asteroids can become hazardous. The cost of maintaining this system is modest compared to the protection it provides. NEO surveyors' operational costs after launch will be tens of millions per year, comparable to operating a large ground-based telescope. Ground-based survey programs cost similar amounts. The Planetary Defense Coordination Office operates on a budget of around 150 to 200 million per year total, including detection programs, orbit calculation, and mission planning. For context, the United States spends about $850 billion per year on military defense. The NEO program is about 0.02% of that. We spend more on individual weapon systems than we do on the entire planetary defense budget. Scaling up to a fully robust system might require doubling or tripling current funding, but we're still talking about a fraction of a percent of overall defense spending. And unlike military threats, which are adversarial and constantly evolving, as potential enemies develop new technologies, asteroids are non-adversarial. They follow predictable laws of physics. Once detected and tracked, they don't maneuver to evade detection or develop countermeasures to deflection attempts. The problem is technically simpler than many military challenges, and the solution is more permanent. Once an asteroid is deflected, it stays deflected. From a cost-benefit perspective, planetary defense might be the most favorable investment a civilization can make. The cost is low, the technology is proven, and the risk reduction is substantial. But beyond the practical arguments, there's something profound about developing planetary defense capabilities. For the first time in Earth's history, one species has the ability to prevent natural disasters on a geological scale. Asteroid impacts have been shaping Earth's environment for billions of years, causing mass extinctions, altering climate, redistributing species. Until recently, life on Earth was at the mercy of these cosmic accidents. Now we can do something about it. We can detect asteroids decades before they hit. We can calculate their trajectories. We can launch spacecraft to intercept them. We can change their orbits. We can protect not just human civilization, but the entire biosphere. This is an extraordinary capability. It places humanity in a fundamentally different relationship with nature. We're no longer passive recipients of whatever the cosmos throws at us. We're active agents who can shape our planet's future, and with that capability comes responsibility. If we have the ability to prevent asteroid impacts and choose not to, if we detect a hazardous asteroid decades in advance, have time to deflect it but fail to do so because of budget constraints or political dysfunction, then the resulting catastrophe isn't just a natural disaster, it's a preventable tragedy. The deaths aren't random misfortune, they're a consequence of our choices. That's a sobering thought. We're approaching a point where major asteroid impacts transition from acts of God to failures of policy. If a 700-meter asteroid hits Earth in 2050, and we could have prevented it but didn't because we delayed NEO Surveyor by 5 years, the responsibility falls on us. Future generations will judge us by how we handle this. Did we take the threat seriously and invest in detection and deflection? Or did we ignore the warnings, delay the necessary programs, and leave civilization vulnerable to preventable catastrophes? Right now, we're in a middle state. We've made progress. We have detection programs. We've tested deflection technology. We're building NEO Surveyor. But we're also leaving gaps. The blind spot remains open. Thousands of hazardous asteroids are undetected. The timeline for completing the congressional mandate has slipped by decades. We can do better. We have the resources, the technology, and the knowledge. What's needed is the will to prioritize planetary defense at a level commensurate with the risk. And maybe, ironically, the media attention on 3IATLAS can be redirected toward the real threat. When people look up at the sky and think about objects from space, they should be thinking about near-Earth asteroids in the sun's blind spot, not distant interstellar visitors. When Avi Loeb talks about cosmic threats, he should be emphasizing the undetected 700-meter asteroids hiding in twilight, not speculating about the nature of objects millions of miles away that pose zero danger. There's room for both scientific curiosity about interstellar visitors and practical concern about near-Earth hazards. But the balance has been off. We've been fascinated by the exotic and distant while neglecting the immediate and dangerous. The sun's blind spot is real. The undetected asteroids are real. The risk is real. And the solution, NEO Surveyor, NEOMEA, kinetic impactors, comprehensive surveys, is within our grasp. All we have to do is commit to it. Launch NEO Surveyor on schedule, fund follow-up observations, maintain detection networks, prepare deflection capabilities. Treat planetary defense as the essential infrastructure it is, not as a nice-to-have program that can be delayed whenever budgets are tight. If we do that, then 20 years from now, we'll have a comprehensive catalogue of near-Earth asteroids. The blind spot will be closed. Hazardous objects will be known decades before they pose a threat. Deflection missions will be routine, boring even, just another spacecraft launch, another successful orbit change, another averted disaster that nobody notices because it never happened. That's the future we should be working toward. A future where asteroid impacts join smallpox and plague as threats that once menaced humanity but have been effectively eliminated through technology and foresight. We're closer to that future than ever before. NEO Surveyor is being built. DART-proof deflection works. The technology is ready. The only question is whether we'll finish the job or whether we'll keep delaying until luck runs out. Let me bring this back to where we started. While the world watches 3IATLAS, that distant interstellar visitor millions of miles away, harmlessly passing through the outer solar system on a trajectory that will never threaten Earth, hundreds of asteroids lurk in a blind spot we've known about for decades. Some of them are larger than the Tunguska impactor. Some are the size of 225 SC79, 700 meters of rock and metal, carrying enough kinetic energy to devastate a continent, and we don't know where they are. This isn't a hypothetical problem. Scott Shepard found 225 SC79 in September 2025, hiding in the sun's glare, undetected despite decades of surveys. The Chelyabinsk meteor injured 1/500 people in 2013, approaching from the sun's direction with zero warning. The asteroid 223 NT1 passed within 100,000 kilometers of Earth in July 2023 and wasn't detected until 2 days after it had already passed us. These events keep happening because we have a systematic blind spot in Earth's asteroid detection system. Ground-based telescopes can't effectively observe near the Sun due to atmospheric interference and the Sun's overwhelming brightness. Space-based telescopes like Hubble and JWST avoid pointing near the Sun to prevent damage. The result is a massive dead zone where asteroids can hide undetected until they're already making close approaches to Earth. Congress recognized this problem 20 years ago when it mandated that NASA detect 90% of near-Earth asteroids larger than 140 meters by 2020. We missed that deadline. We're currently at about 40% completion. Without a dedicated space-based infrared telescope, we might not reach 90% until 2040 or later. 2 decades late. NEO Surveyor is that telescope. It's designed specifically to observe at the L1 Lagrange point between Earth and the Sun, using infrared detectors that can see asteroids by their thermal emission rather than reflected sunlight. It will scan the entire sky every 2 weeks, building a comprehensive catalogue over 10 to 12 years. It will find the Ateras and Vateras hiding inside Earth's orbit. It will detect asteroids approaching from sunward directions. It will finally fulfill the congressional mandate, but it has been delayed repeatedly. Originally planned for a mid-2020s launch, it's now scheduled for late 2027 or early 2028. The cost has doubled from $500 million to $1.2 billion, not because the telescope got more expensive, but because delays add costs while delivering no additional capability. And there's always a risk of further delays. Budget cuts, technical problems, launch vehicle availability. Meanwhile, the DART mission proved that we can deflect asteroids. On September 26, 2022, NASA deliberately crashed a spacecraft into the asteroid Dimorphos and changed its orbital period by 32 minutes, far exceeding the mission's success threshold. We now have experimental proof that kinetic impactors work, and work better than conservative models predicted. So we have a paradox. We've proven we can defend against asteroid impacts, but we can't use that capability if we don't see asteroids in time. We have the solution to the problem, but we're not implementing the detection system needed to make it work. Every year of delay matters. Some of the asteroids currently hiding in the Sun's blind spot are on trajectories that will bring them close to Earth in the 2030s or 2040s. If we find them in 2029 with NEO Surveyor, we have time to plan and execute deflection missions. If we delay the mission by 5 years and find them in 2034, the timeline gets tighter. If we delay by 10 years, we might discover asteroids that are already too close to deflect. This is preventable. Unlike pandemics or climate change, or other emerging threats that require changing human behavior or solving complex social problems, asteroid defense is technically straightforward. We know what needs to be done. We have the technology. We just need to build it and launch it. The cost is modest. NEO Surveyor's $1.2 billion price tag, spread over a decade, is less than what's spent on countless other programs. A single 700-meter asteroid impact would cause trillions in damage and kill millions of people. The cost-benefit ratio is overwhelmingly in favor of investing in detection and deflection. And this isn't just about preventing a single disaster. It's about taking responsibility for Earth's future. For 4 billion years, life on this planet has been at the mercy of cosmic accidents. Asteroid impacts have caused mass extinctions, reshaped continents, altered climate. Now, for the first time, one species has the ability to prevent these disasters. That's an extraordinary transition. We're no longer passive recipients of whatever the universe throws at us. We're active agents who can protect our planet and everything living on it. But with that capability becomes responsibility. If we have the power to prevent asteroid impacts and choose not to, if we delay the necessary programs, underfund detection systems, fail to launch deflection missions when needed, then the resulting catastrophes aren't acts of God. They're failures of leadership, policy, and priorities. The comparison to 3IATLAS makes the misallocation of attention even more stark. That interstellar visitor is fascinating scientifically, absolutely worth studying, but it poses zero threat. It's 126 million miles away at closest approach, fully tracked, leaving the solar system. We know exactly where it is and where it's going. The twilight asteroids are different. They're close. Some cross Earth's orbit, many are undetected, and unlike 3IATLAS, they're actually dangerous. A 700-meter Atira asteroid on the wrong trajectory could end modern civilization. Yet the media obsesses over the distant, harmless object, while the real threat lurks unseen in the sun's glare. This is the contrarian angle that should be getting attention. We're looking the wrong way. The existential threat isn't the exotic interstellar visitor millions of miles away. It's the undetected near-Earth asteroids hiding in the blind spot, some of them already on trajectories that will bring them terrifyingly close in the coming decades. And we're running out of time. Not in the sense that an impact is imminent. The probability in any given year remains low, but in the sense that every year of delay makes the problem worse. Every year without any surveyor is a year where hazardous asteroids remain undetected, and the window for deflection grows narrower. Consider the timeline. If NEO Surveyor launches in late 2027, it reaches L1 and begins operations in early 28. Over the next 12 years, it completes its comprehensive survey, reaching the 90% detection threshold around 2040. Any asteroid discovered in, say, 2032 that's on a collision trajectory for 2055 gives us 23 years to prepare and execute a deflection mission. That's comfortable. Plenty of time to design the mission, build the spacecraft, launch it, perform the deflection, and verify the results. But if NEO Surveyor is delayed to 2032 and doesn't complete its survey until 2044, then the same asteroid isn't discovered until 2037, giving only 18 years to impact. Still workable, but tighter. And if the asteroid is on a faster collision trajectory, or if there are technical delays in the deflection mission, that 18 years might not be enough. This is the gamble we're taking with every delay, that we'll have enough warning time when we finally discover the hazardous asteroids. Maybe we will. Maybe all the dangerous objects have orbits that won't threaten Earth for a century or more, giving us plenty of time even with delays. But maybe not. Maybe there's a 500-meter asteroid hiding in the sun's glare right now, on a trajectory that will impact Earth in 2043, and we won't find it until 2035, leaving only 8 years to mount a deflection mission. That's cutting it dangerously close. We don't know. That's the whole problem. The asteroids in the blind spot are, by definition, invisible to our current detection systems. We can estimate how many there are based on population models, but we don't know their specific orbits. We don't know which ones pose threats and which are harmless. We won't know until NEO Surveyor surveys the region and catalogues what's actually there. And that uncertainty should be motivating. We're flying through a cosmic shooting gallery with a blindfold over part of our field of vision. Some of the bullets are 700 meters across, traveling at 20 kilometers per second, carrying enough energy to devastate continents. Taking off the blindfold seems like an urgent priority, yet here we are, in November 25, still waiting. NEO Surveyor is being built, which is good, but it should have launched years ago. The congressional mandate should have been fulfilled in 2020. We're half a decade behind schedule, and thousands of hazardous asteroids remain undetected. The path forward is clear. Launch NEO Surveyor on schedule in late 2027. Maintain full funding through its operational lifetime. Support ESA's NEOMEA mission to provide complementary coverage. Expand ground-based surveys to handle the flood of new discoveries. Prepare deflection missions based on DART's proven design. Treat planetary defense as critical infrastructure, not as a discretionary program that can be delayed whenever budgets get tight. Do all that, and by the 2040s, Earth will have comprehensive protection against asteroid impacts. The blind spot will be closed. Hazardous objects will be catalogued decades before they pose threats. Deflection missions will be routine. Future generations won't have to worry about random, cosmic disasters ending civilization. But we have to finish the job. No more delays, no more budget cuts, no more treating the only and legally mandated NASA program as lower priority than discretionary missions. The Sun's blind spot has hidden threats long enough. 2025 S79 proved that 700-meter asteroids can lurk there undetected for years or decades. The Chelyabinsk meteor proved that objects approaching from the Sun's direction give zero warning. The 2023 NT1 flyby proved that even modern detection systems can miss large objects until after they've already passed. We know the problem, we know the solution, we just need to implement it. And in the meantime, when people ask what you're worried about in space, don't talk about 3IATLAS. Talk about the undetected asteroids in the Sun's glare. Talk about the blind spot that could hide a planet killer until it's too late. Talk about NEO Surveyor and why it needs to launch on schedule. Talk about the congressional mandate we're 5 years late on and still not close to fulfilling. That's the story that matters. That's the threat we need to address. That's where our attention should be focused. Because 3IATLAS is a curiosity, a scientific puzzle, a fascinating visitor from interstellar space. But it's not dangerous. It's never been dangerous. It will pass through the solar system and disappear into the cosmic void, and Earth will be exactly as safe as it was before. The twilight asteroids are different. They're here, they're close. Some are large enough to end civilization, and most of them are still hiding, undetected, in the one place our telescopes can't easily look. That's the blind spot that could end everything, and we're running out of time to close it. So here's where we stand in November 2025. Congress mandated in 2005 that NASA detect 90% of near-Earth asteroids larger than 140 meters by 2020. We're 5 years past that deadline and only 40% complete. Thousands of potentially hazardous asteroids remain undetected, many of them hiding in the Sun's blind spot where ground-based telescopes can't effectively observe them. Scott Shepard discovered 225 S79 in September 2025, a 700-meter asteroid hiding in twilight, undetected until that moment, despite decades of surveys. It's the second fastest asteroid in the solar system, orbiting mostly inside Earth's orbit, exactly the type of object our detection systems systematically miss. And it's large enough to cause continental-scale devastation if it ever hit Earth. NASA's NEO Surveyor mission, specifically designed to close the blind spot, has been delayed from its original mid-2020s target to late 2027 or early 2028. Its cost has doubled due to funding delays. It's the only program NASA is legally mandated to complete, yet it keeps getting deprioritized when budgets are tight. The DART mission proved in September 22 that we can deflect asteroids using kinetic impactors. The technique works better than predicted. We have a proven deflection method, but it only works if we have decades of warning time. Find an asteroid 20 years before impact, and deflection is straightforward. Find it 5 years before, and it becomes extremely difficult. Find it days before, like Chelyabinsk, and there's nothing we can do. Meanwhile, the media and public attention focuses on 3IATLAS, an interstellar comet 126 million miles away that poses zero threat to Earth. It's scientifically interesting, absolutely worth studying, but harmless. The real danger, thousands of undetected near-Earth asteroids, some potentially on collision trajectories, goes largely ignored. This misallocation of attention and resources needs to change. The sun's blind spot is real. The asteroids hiding there are real. Some of them are large enough to devastate continents or end civilization, and we're gambling that we'll find them in time to deflect them. That gamble gets riskier with every year of delay. NEO Surveyor needs to launch on schedule. It needs full funding throughout its operational lifetime. Follow-up deflection missions need to be prepared and ready to deploy when hazardous asteroids are discovered. Planetary defense needs to be treated as the critical infrastructure it is. The stakes couldn't be higher. We're talking about protecting human civilization and Earth's entire biosphere from preventable cosmic catastrophes. The cost is modest, a few $1 billion spread over decades. The technology is proven. The only thing lacking is the political will to prioritize it appropriately. So the next time someone mentions 3IATLAS or any other distant space object, redirect the conversation. The real story isn't the exotic interstellar visitor, it's the blind spot. It's the undetected asteroids in the sun's glare. It's the 700-meter objects that could end civilization, and we won't see coming unless we build and launch the telescopes designed to find them. It's the choice between being ready or being surprised, between detection and deflection, or evacuation and catastrophe, between taking responsibility for Earth's future or leaving it to cosmic chance. The clock is ticking. Every day without comprehensive asteroid detection is a day of unnecessary risk. Every delay to NEO Surveyor narrows the window between discovery and potential impact. Every year, we focus on harmless, distant objects, while ignoring near-Earth threats is a year wasted. We have the knowledge, we have the technology, we have the resources. What we need now is the urgency to match the scale of the threat. The sun's blind spot has hidden dangers long enough. It's time to shine a light into that darkness and catalogue what's actually there. Before luck runs out, before we discover a hazardous asteroid too late to deflect it, before a 700-meter rock slams into Earth at 20 kilometers per second and reminds us catastrophically that some threats can't be ignored. The choice is ours, and the window to make it is closing. Thanks for staying with me through this investigation. If this deep dive into Earth's asteroid detection blind spot convinced you that this deserves more attention than distant interstellar visitors, hit that like button and subscribe. Share this with anyone who thinks 3IATLAS is the cosmic threat we should be worried about. The real danger is closer than most people realize, and it's time we started looking in the right direction. Drop a comment with your thoughts. Are you convinced NEO Surveyor is critical? Do you think planetary defense deserves more funding? Should NASA be held accountable for missing the congressional deadline by 5 years? Let me know what you think. And remember, when you look up at the sun, you're looking at the blind spot that could hide a civilization-ending asteroid. Until NEO Surveyor launches and completes its survey, we won't know what's actually there. That should terrify you more than any harmless interstellar visitor ever could. Stay curious, stay vigilant, and keep looking up, especially where our telescopes currently can't.